Hi everybody. In this video we're going to look at oxygen, hydrogen, nitrogen, and the halogens. We're going to start off with oxygen. Oxygen means acid former. It was named actually in 1775 by a French chemist who noticed that oxygen would combine with a lot of different substances to form acids, and so he named it oxygen. If we look at the natural occurring amounts of oxygen, it is the most abundant element on Earth, not in the universe, but on Earth anyway. In the air, it makes up about 21% by volume. Most of the air is actually nitrogen. In water, it makes up about 89% of the mass of water, because again, it's a bigger molecule than hydrogen. It's the most abundant element by mass in the Earth's crust and in the human body. Again, the human body is mostly water, so it would make sense that oxygen makes up the vast amount of our body. You find two natural forms of oxygen. Oxygen has two allotropes. An allotrope is an element that is in different chemical forms, but in the same physical state. So, for instance, dioxygen and ozone for oxygen are the two allotropes. They are oxygen and they're gases, but they're just in different chemical forms. Dioxygen, or O2, is what we breathe. This is the form that is most commonly found in nature. You can freeze it, you can condense it at pretty low temperatures, but this is what you would normally find when we talk about oxygen. This is dioxygen. The other naturally occurring allotrope is ozone, O3. The ozone layer is named that because that's where ozone goes and it absorbs photons. Ozone is created through lightning strikes. If you've ever quote-unquote smelt electricity, what you're smelling is the electrical currents turning dioxygen into ozone, so you actually smell the ozone. If we look at the characteristics of oxygen, its physical properties include it being a colorless, odorless, tasteless gas. Gas is its natural form. Again, it can be condensed or frozen from a gas to a liquid to a solid, but at very low temperatures and pretty high pressures. It is heavier than air, slightly heavier than air. That's why oxygen on Earth is found at the lower latitudes. That's the biosphere where animals live. It is slightly soluble in water, so will dissolve in water a little bit. That's good for fish because that's how fish breathe. And as I mentioned, you can liquefy it and solidify it at extreme pressures and very low temperatures. You'd have to go negative, I think it's like 180 to liquefy it, 180 degrees Celsius. So it's real cold to get it to liquefy and solidify. Its chemical properties include being highly reactive. It has a fairly high electronegativity. Again, electronegativity is the ability of an atom in a molecule to attract electrons. The reactions of oxygen are pretty slow at normal temperatures, but as you elevate the temperature, its reactivity goes up, and that's the reason that it supports combustion. It's probably the main supporter of combustion on the Earth. Again, combustion is burning. It's rapid oxidation. And it acts as an oxidizing agent. An oxidizing agent is something that is reduced in a redox reaction. We'll see the definition of a redox reaction in a minute. The main reactions involving oxygen would include oxidation. Now, we've looked at oxidation, the definition before, as increases in oxidation number or loss of electron, but there's actually two more definitions. You can define oxidation in four ways: either the addition of oxygen to something, the removal of hydrogen from something, loss of an electron, or an increase in oxidation number. And one of the reasons why you say loss of electron from oxidation is that when you add oxygen to something, it's so electronegative that it actually steals an electron from something. Now, that loss of electron can also be due to light. So if you put like car interiors or something like that in the sunlight, they will fade over time, and they fade because the photons of the light is actually knocking electrons off the molecules of whatever the substance is that fades. And that's also a version of oxidation. Another reaction that it goes through is combustion. We've mentioned combustion before. It's rapid exothermic oxidation, or burning. Exothermic means that it gives off heat. And so when things burn, they're combining with oxygen at a rapid pace, and that's what's causing them to burn. Next up is hydrogen. Hydrogen means water producer. Hydro, water, gen, to produce. Natural occurring amounts of hydrogen. It is the most abundant element in the universe. All elements have kind of been created through hydrogen kind of smashing together. Though it is the most abundant element in the universe, which comprises about 70% of the universe, there is very little free hydrogen, mainly because hydrogen reacts very quickly with things. You don't see a lot of clouds of hydrogen just kind of floating around. It is also the main component of tissue gas. Tissue gas is the gas that is produced through decomposition. That's what makes bodies bloat up, and hydrogen is the main component of that. Now, hydrogen has some isotopes that are kind of interesting. If you remember, an isotope is an atom that has more or less than the normal number of neutrons in it. So it's lighter or heavier, more mass or less mass. So the isotopes of hydrogen, one is protium. Protium is pretty much the normal hydrogen molecule that floats around, comprises about over 99% of the naturally occurring hydrogen. It's kind of an interesting isotope in that its nucleus for protium is only a proton. There's no neutrons in protium. If you add a neutron to it, to the nucleus, then you'd get deuterium. Deuterium is a single proton and a neutron. This is it is a naturally occurring isotope, but it's less than 0.15%, so it doesn't happen very often. But deuterium is used to make heavy water. Heavy water can be used then to make tritium. Tritium is in the nucleus is a proton and two neutrons, and where tritium is important is that it's radioactive. It has a half-life of about 12 years or so. It's the main source of power for thermonuclear weapons, and so that's when they're making the fuel for nuclear weapons. They're going to go from protium to deuterium to tritium. If we look at the characteristics of hydrogen, its physical properties, it is a colorless, odorless, tasteless gas. It is lighter than air. That's why it can be used to float things. In class, I mentioned the Hindenburg, the dirigibles, the Zeppelins, the blimps. Those had originally had hydrogen gas in them. Now they use helium, but back in the day they used hydrogen. Its chemical properties, it does burn. It burns with a hot blue flame. It forms water, or helps to form water. Technically, it doesn't support combustion, but it will burn if there's oxygen around. And it acts as a reducing agent. So because hydrogen is a reducing agent, its reaction is reduction. If you look at the definition of oxidation that we just had under the oxygen section, put that in reverse and you get reduction. Reduction is the adding of hydrogen to something, the removal of oxygen from a substance, gaining electrons, or if you gain electrons, then you will decrease the oxidation number. And the reason why something would gain electrons is because when it adds hydrogen, hydrogen has such a low ionization energy, it doesn't take a lot of energy for it to lose its electron, and so whatever it's kind of reacting with is going to gain that electron, and so it gets oxidized, or pardon me, it gets reduced, the oxidation number goes down. Now, when something gets oxidized and or reduced, something else is going to also get oxidized or reduced. So that's what we call a redox reaction. Oxidation and reduction take place at the same time. So an example would be, let's see if I can draw it out here. So let's see, N2H, it's hard to draw, 4 plus O2 This is a oxidation reduction reaction. So if this is what we call hydrazine, N2H4, and you add that to oxygen, what you get out of it is N2 plus 2H2O. So what happened here? Well, the hydrogen from the hydrazine came off and attached to the oxygen. So what happened? The hydrazine lost hydrogens, okay, so that got oxidized. The oxygen gained hydrogens, so that got reduced. Okay, so this got oxidized because it lost hydrogen. This got reduced because it gained hydrogen. That's what a redox reaction is. So anytime oxidation takes place, reduction will also take place. The next element we're going to look at is nitrogen. Now, nitrogen is important to us because this is the element that formaldehyde and glutaraldehyde interact with to cross-link proteins. So it is the most abundant element in the Earth's atmosphere by volume. Hydrogen is still the most abundant element in the universe. Oxygen is still the most abundant element on Earth, but nitrogen is the most abundant element in the atmosphere. Its properties, its melting point is about 210 degrees, minus 210 degrees Celsius. So that I can get it, I can actually liquefy it at that point. That's where you get liquid nitrogen from in like those cooking shows. It's the fourth most electronegative element, so it has a pretty good pull on electrons, and it forms ammonia, NH3. And the ammonia part, the nitrogen, again, that's where molecules of formaldehyde are going to interact with proteins, because all proteins have nitrogen in them. So next up, we are going to look at the halogens. The halogens are the elements of group 17. So if you look at the periodic table, there's 18 columns all the way across. The halogens are in the ones that, in the 17th column, right next to the noble gases. So they're one off from the very end. They include chlorine, fluorine, bromine, and iodine. These all have, why they kind of make them their own little group is that they all have 7 valence electrons and high electronegativity. So they pull real hard and they only want 1 electron. So they're pretty reactive elements. So if we look at the characteristics of the halogens have a melting and boiling point that increase with the increasing atomic number. So for instance, the boiling points are kind of probably the important part, because fluorine and chlorine at room temp are gases. Bromine is a liquid. Iodine is a solid. So when you have iodine solutions, they've kind of suspended them in either surfactants or alcohols. All are diatomic molecules, naturally occurring that way. You find them in nature pairing up with each other. So you don't just see a fluorine by itself. You see Fl2. You don't see chlorine by itself. You see Cl2. Same with bromine and iodine. And the reason why they do that is it gives each other an octet. So they're very easily made happy that way. As I mentioned, they have very high electronegativity. Electronegativity increases as you go right and up on the periodic table. And that's why fluorine is the most electronegative element. And they will often react with metals to form salts. So for instance, in this case, we have sodium and chlorine mixing together to turn into sodium chloride, or table salt. So the halogen that probably makes the most effect on us anyway in embalming is chlorine. Now, when you put chlorine, pure chlorine, with water, it will react very slowly to form aqueous solutions of hydrochloric acid and hypochlorous acid. This is how you do it. You take, again, chlorine, add it to water, and you'll get hypochloric acid here and hypochlorous acid here. Now, the hydrochloric acid is the strongest of the acids. It's got a very, very low pH, about a pH of 2, roughly. Hydrochloric acid is actually one of the main components in your stomach acid. The hypochlorous acid, this is the component that will oxidize bacteria. That's why they use chlorine to sterilize water, especially in like pools. When they shock a pool, they'll put chlorine in there, and it's going to make this hypochlorous acid that oxidizes the bacteria. Now, technically, it's going to kind of move around. It's got hypochlorous acid. It will be kind of hypochlorite somewhat a little bit too. Hypochlorous acid is actually a fairly weak acid compared to hydrochloric acid. But again, this is one of the main components of disinfectants for pools. Sodium hypochlorite, or bleach, as it's kind of commonly known, NaOCl, is the active ingredient in many bleaches and is oftentimes used to as a disinfectant. We should never use it for disinfecting in the prep room, though, and that's kind of why we talk about chlorine. Never used with formaldehyde or organic materials. Both of them, well, formaldehyde is an organic material, and sodium hypochlorite reacts very violently with organic materials. It creates chlorine gas, which if you inhale will turn into hydrochloric acid in your lungs, but it also creates something called haloforms, chlorohaloforms, which are highly carcinogenic. And so if you disinfected your prep room a lot with bleach, you're going to end up giving yourself cancer over time. So that's why we talk about chlorine, to make sure that you avoid it. That finishes it up for this section. In the next section, we're going to start looking at the various aspects of water and how it affects the embalming process.